So welcome back to Computer Science 4303. Today we are going to be talking more about procedural content generation and specifically some stuff that you should know for assignment 3 that will be released in 2 days on Thursday. So today we're going to be talking about procedural content generation for things like terrain, and we're going to be using two different methods. One is called Cellular Automata and the other is called Perlin Noise. So let's jump into some PowerPoint slides that I have. And I'm not sure how long today's lecture is going to be because it's going to be a mixture of a little bit of demo, a little bit of slides, and then you can take stuff from this and apply it to the next assignment, and I think that'll be pretty fun. So let's go to the PowerPoint and we'll get started. The laser pointer up here. So yeah, this is lecture number 11. First, we're going to talk about cellular automata for the purposes of procedural content generation. We could have an entire course on cellular automata, and then we're going to talk a little bit about Perlin Noise. So let's go. So one issue that we saw before is that pure randomness is what we want, right? So one issue with using randomness for PCG is that sort of pure randomness is unappealing. If we just throw random things on the screen, human brains don't deal well with pure randomness. We don't find it nice. So what we really want is we want some methods to generate content for gameplay, whether that's like mechanical gameplay or environments that we can play in, etc. And those things should have some sort of human intuition or coherence, but use the randomness that we talked about last time for variety, okay? So what we're going to do, and what we're going to see as a pattern in procedural content generation, is we're going to generate some sort of random data as a starting point, and then we're going to use some other method to sort of shape that random data into something that we would actually want to use for our game. So let me just show you some examples of like randomness and then shaped randomness and show you what we're talking about. So here's an example of random noise, okay? So this is actually not quite random, but it's random enough to be kind of unappealing. Like things are just thrown all over the place and it doesn't really look like something we could play a game in, right? It looks kind of like a maze. But if we take this random noise and we shape it using something like a cellular automata, for example, we can turn this random noise into this. And this has some sort of intuition to at least to a gamer or a human being that says, oh, that looks like some sort of cave system, or maybe a dungeon for a game or something like that. So this is what we did. With our method of cellular automata that we're going to see, we're going to take an initial seed of randomness like this, and we're going to shape it somehow and turn it into something that we would want to use. In the second half of the lecture, we're going to see Perlin Noise, and Perlin Noise is way more complicated than the cellular automata we're going to do. But with Perlin Noise, we could start generating some really crazy, cool looking stuff. So today, that's what we're going to be doing. We're going to be turning pure randomness into things like this and into things like this in ways that are, you know, and the end product will be something that we could possibly use in our game. So first, what is a cellular automata? Anyone out there in the chat that's used a cellular automata before or knows what they are? I only saw them in one course in computer science, and it was another fourth-year course. So it's very possible that people haven't seen this before, and it's a truly fascinating subject. Someone said the game of life. Yes, that uses cellular automata, and we're going to talk about that for a little bit. So a cellular automata, or a CA, I'm probably going to call it from now on, it's a discrete model used for performing various types of computation. So what I mean by various types of computation is that CA are actually shown to be Turing complete. So you can use a CA to compute anything that is computable. However, in practice, that ends up being this gigantic theoretic and practical mess involving like thousands and thousands and thousands of cells, and it looks really ugly. So in practice, you would not use a cellular automata to actually like implement a general purpose CPU or something like that. They can be used for implementing games, for implementing pattern or texture generation, and many other things. So what they are at their core, and up here there's an example of a cellular automata running up here, and we'll show how this actually works. What they actually do is that a CA, they're defined by a series of rules or conditions, and that translate some points on a grid of data into a new grid of data. Okay? So for example, if you take this up here, if you take it frame by frame, one frame, there is like a picture, that's a grid of data. You're going to use some rules to translate that grid of data into a new grid of data, and if you play those grids in sequence, you get this interesting animation. So let's talk about how that works. So one-dimensional cellular automata. So Stephen Wolfram wrote a book called A New Kind of Science, in which he goes for hundreds of pages about cellular automata. It's a really fascinating book. Wolfram comes off as very eccentric in it, but he makes some amazing stuff. If you've ever heard of Wolfram Alpha, then that's the guy who made Wolfram Alpha, the website, and his book is really cool. He called 1D cellular automata elementary CAs. So what are they? Given a grid, a one-dimensional grid, so like an array. So whenever I say 1D grid, that's an array with cells marked 0 or 1. So you're given this 1D grid. Some of them are going to be black, some of them are going to be white, or some of them are going to be true or false, or on or off, or alive or dead. However you want to represent it, you're given an array of Boolean values. For each cell in that array, you're going to look at that cell and the two surrounding neighbors. Okay, so you're looking at three cells. You're looking at yourself, you're looking at your neighbor to the left, and you're looking at your neighbor to the right. Based on the values of those three cells, we either turn on or off the next generation's cell. Okay, so let's look at how that works. So an elementary CA, if you have a one-dimensional array, okay, so this is an example that we can look at. Oh, and I'm covering it up, of course. So let me move myself down here via the magic of television. So up here, what we have, if we think about it, we have, if we're considering our cell, the cell to the left, and the cell to the right, so that's three cells. Each of those three cells can have one of two different values, so that's 8 possibilities for any one cell and the surrounding two cells. So what we have here is a mapping from any of those three combinations of off, 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 on, off, on, off. So all 8 combinations of 3 cells. And what we've listed underneath is an example of what we could do if that comes up. So what we're going to do here is we're going to take this top row of cells, okay? So step 1, we're just looking at the top row here. I know that this is a 2-dimensional grid, but what we're going to be doing is generating each subsequent row of this picture one at a time using this rule, okay? So what we do is we start at the top row where we have all blank cells except one cell right in the middle. And then we apply this rule to generate the next row. So let's look at that rule that we just did. And I think I have my blackboard somewhere. Do I? Let's see. Okay. So, oh, I don't have a thing for my blackboard. All right. Here's the blackboard. Nope. That's not working properly. Weird. Oh, okay. I see why. There we go. There's my blackboard. All right. We're back in it. No! What's happening? Hang on a second. I'm getting back to a working blackboard. Oh, it's broken. Oh, I know why. Okay. We're doing it live. We're doing it live. Okay, working blackboard. Thank God. All right. So here, what we have is we're going to have an array of values. Okay. So let's draw an array of values. Let's do it like this. We've got some number of values. Okay, so now we're going to fill in a couple of these. Let's say these two are filled in. Hang on a second, I forgot to draw that line there. All right, so we've got this is on, maybe this is on. Okay, so what we do is we might have a rule that says if we see off, off, on, then the next cell down here in our next row, this one is going to be turned on, for example. Or if we see off, on, off, then this one is going to be off. So what we do is we start with one row, and then we generate the next row. Okay, so that was my scuffed version of how we're going to be doing this. Let's go back to the PowerPoint before I make a fool of myself. All right, so we're starting at this row. Let me get the pen out. Okay, and then we go through it, and we use these rules to generate the next row. So let's look at these rules. Here we have, and I know this is kind of small, but you kind of have to be a little bit small. Here we have 3 cells in a row that are on, or I guess ones are black. So this is off, 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 0, 0, 0. So if we see, if we want to know what to do, right? So what will we do for this cell right here underneath it? Well, we look up here, we see this rule applies. So we see blank, 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 and we put in a blank. Okay? Then we go to the next one, we see blank, 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 we put in another blank, and it's all, you know, it's all blank, 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 until we get right here to blank, blank, black. Okay? So 0, 0, 1. So we look up at our rule, and we see, okay, 0, 0, 1, if we ever see that, we put a 1 underneath it. So we see 0, 0, 1, we put a 1 underneath it. Next, we have 0, 1, 0. So we look up here, we see 0, 1, 0, and we put a 0 underneath it. Next, we have 1, 0, 0, we put a 1 underneath it. And so we use these rules. Once we've computed that row, then we use that computed row to compute the next row. Then we use the next row to compute the next row, and we iteratively apply the rule to generate subsequent rows, okay? And so what we have here, one way that we can name these rules is that if we take this rule up here and we fix the orderings of the patterns and we count the binary here, so 0, 1, 0, 1, 1, 0, 1, 0, then what we get is 90. So we can call this one rule 90, all right? So we can number the rules of elementary one-dimensional cellular automata in that way. So if you ever see rule 90 or rule 260 or 215 or rule 7, that's how it's generated. So you take the patterns in this order, you put down the binary representation of that rule, and you move on. Oh, here we go. I had a slide for this, and I forgot. So excuse me. Excuse me for that, like, really scuffed last slide. All right. Someone asked, how did we get a black cell at the bottom left corner? Sometimes what we do is we wrap around. We wrap around the edges. So it's like a torus, right? So we don't treat it like that. We would say, like, we take this one, and this one. So that's how we do that wraparound. So here's an actual animation of it happening, where we look at each block of 3, we see what that rule tells us to do, and then in our next row, we actually apply that. So maybe I should have this slide first. That would make a whole lot of sense, hey? So let me just play this through so you can see how that works a little bit. So that's what we do. We take an array of values, we look up the rule, and then we apply that rule. And someone just said rule 30 is my favorite, and then we switched, and now there's rule 30. So maybe rule 30 has something interesting with it. So if we want to look, this slide comes from Wolfram's book, where he enumerates all of the interesting rules. It turns out that most of the cellular automata rules, they just end up in all black or all white, and so they're not super interesting. So what he did was list some of the interesting rules and some of the starting patterns that create interesting values. Like if you look back at Rule 90, does anyone know the name of this pattern that it created? You should probably know it. Let's see if someone is able to type that out. There are lots of patterns similar to that that end up getting generated. So yeah, someone said Sierpinski's triangle. That's exactly what it is. And you can see here that Rule 90 does, from a single block, create Sierpinski triangle, but many others come close to it. And that's because of the fractal nature, sort of the recursive fractal nature of how cellular automata are defined. They're very likely to end up producing these sort of fractal geometries. Okay, so that's what a cellular automata is in one dimension. Now, what is a 2D cellular automata? Well, they're similar to 1D, but they're on a 2D grid, okay? So what you're doing is instead of just choosing your left and right neighbors in a cell to go along with yourself, you're choosing a neighborhood around the cell. And so based on a set of rules, that cell will either be alive or dead in the next grid. So before, what we had, if I can show you again, is we took one line, right? We took one array and we generated a new array. What we end up with from that is we take one line, we generate the next, we generate the next, we generate the next. In a 2D version, we're going to take one two-dimensional grid and then create another two-dimensional grid. Okay. So what we end up with is a three-dimensional structure, but kind of more interesting than a three-dimensional structure, we can come up with a two-dimensional animation because that's how our brains are able to view it in a more interesting way. So based on a set of rules involving the neighbors around itself in this two-dimensional grid, the cell that was either alive or dead in one grid will be alive or dead in the next grid. So there are some possible rule choices that you make here. You could say, let's take some specific neighbor conditions. So for example, when we looked at the different rules here, so these rules also exist for two-dimensional cellular automata, and you would just be counting the 9 values around, or the 8 values plus the middle value, so 9 values, and all the combinations of those. And there are, you know, if there's 9 values, what's 2 to the 9? That's 512. So there would be 512 possible rules rather than, no, that doesn't seem right. Is it? No, it's all, yeah, so it's 9 cells. It's one possible or 2 possible values for each one, and all possible orderings of those. So there's lots of them. Okay, I'm not going to go into that then. There's lots of different possible 2D patterns, so we're not going to list those. Okay, so you could have that sort of counted rule like we did with 1D CAs, or you could do something like, let's just count the number of neighbors that are alive or dead, right? It's some sort of condition that you come up with. There's no real rules to this. The fact that it's on a grid and you're counting neighbors and then producing a new value, that makes it a cellular automata. So this is covered super extensively by Stephen Wolfram, as I said, in his book from the 90s, I believe it was the late 90s maybe, called A New Kind of Science. And Wolfram covered a lot about complexity theory and cellular automata, and it was absolutely fascinating. I really like it. I really like that book. The chapter on this is going to be included in the notes. It is free online for you to read if you want to delve more into the extensive, interesting, and eccentric world of Stephen Wolfram and cellular automata. So, now that we have 2 dimensions, the choices become a little bit more difficult, right? They're not more difficult, but they're more varied. So for example, some people have named these type of neighborhoods. So we could have a Moore neighborhood where we look at all of the 8 directions or all of the 8 neighbors in a 2D grid. We could have a von Neumann neighborhood where we only look at up, down, left, and right. And whether or not, and we also have things like hexagonal neighborhoods. So I wanted to include these there because if you look up these online and some people say a Moore neighborhood or a von Neumann neighborhood or whatever, I just wanted you to know what those were. They're just basically up, down, left, right, or 8 directions. And also, your choice of radius matters as well. So if I go back, if we looked at these rules, right, for one-dimensional, we had a radius in 1D equal to 1, right? So we only looked at one neighbor to the left and one neighbor to the right. But of course, if we wanted to, we could look at any number of neighbors to the left and any number of neighbors to the right. There's no real rules with this, even though I'm calling this Rule 30. There's no right way to do cellular automata, right? You can take any amount of neighborhood, you can apply any arbitrary function, and then, but at its most, these are the elementary cellular automata where you have a radius of 1 and you're just checking the 8 possible values. Okay, but in 2 dimensions, people often take a radius that's greater than 1. So if we look at the von Neumann neighborhood, if we have a radius of 1, then we're just looking at the immediate neighbors. If we take a radius of 2, then we're looking at all of our neighbors and the neighbors of neighbors. Okay, so this looks like a breadth first search of depth 2. And similarly with more, it's either all the neighbors or all the neighbors and their neighbors. We could also take some arbitrary neighborhood and say, if we see this exact pattern, right, then we want it to be alive or dead. So it can be as arbitrarily complex as you want, and it turns out that when you apply some thought and interesting rules to this, you end up getting really, really crazy results. And those crazy results, in their most popular form, is called Conway's game of life. So, Conway's game of life is by far and away the most famous cellular automata that has ever existed, right? It's a set of rules based on cellular automata in the background, and that produces some really interesting results. And even people who don't know what a CA is have heard of Conway's game of life. It's a extremely fun programming assignment. If you've never coded up Conway's game of life and you're looking for something to do to brush up on your C++ or whatever, I highly recommend coding up Conway's game of life. It's called Game of Life, not because it's the board game or because it's actually alive, but specific configurations actually do seem to be alive. And what do I mean by alive? Well, they can actually reproduce and consume and die off. And it's really kind of insane. It's like, how do I explain this? I have a weird fascination with this and about how code can seem alive. Like, it's almost like you've created a little universe in which things are living and carrying out their tasks, and then eventually, like, they may reproduce, they may die, they may consume, and how is that really any different than us, right? If anyone was able to create us, they would place just as much value on our lives as any life that we would be able to create. And so it's kind of weird to think about that. It's not a philosophy course. I'll just leave it at that. But I really became kind of obsessed with this notion like many years ago until I decided to just let it go. They're not actually alive, but are they? I don't know. Okay. And all of this can be done with just 4 simple rules. And so here are the rules that Conway's game of life uses. Any live cell with fewer than 2 live neighbors dies, as if by underpopulation. And so when I say as if by underpopulation or something like that, there's not actual like underpopulation going on, but each of these rules, Conway put some sort of human intuitive notion on them. So the rule is any live cell with fewer than 2 live neighbors dies. Now, why might that happen? I don't know. Maybe it's because humans get lonely in real life, or underpopulation, they can't support themselves or whatever. But that's the first rule. The next rule. Any live cell with 2 or 3 live neighbors lives on to the next generation. Okay, so that's the sweet spot where if you're alive, you get to stay alive. Any live cell with more than 3 live neighbors dies, as if there was overpopulation, right? So 2 or 3 was the sweet spot where we continue living. More than 3 and we die. Okay? And that may be, like overpopulation. And any cell with exactly 3 live neighbors becomes a live cell as if by reproduction. So, unlike humans or most life on Earth, there's not 2 parents, there's going to be 3 parents, okay? So, if there's ever a dead cell or a blank cell with exactly 3 live neighbors, then it will become a live cell. And you say, if you've never seen the game of life before, you might say, oh, what do these rules generate? Some surprisingly interesting things. So, you can have, within the Conway's game of life, let me move this down, many interesting patterns. So, these have been sort of categorized by people over the years, because it's been around for 50 years, into a few different categories. Here's just 3 of those categories that I shamelessly stole from Wikipedia. So, one category is the still lifes. And what that means is there are certain patterns that from generation to generation, if these patterns exist, they will continue to exist, and the rules ensure that if they are not modified by external forces, they will continue to exist like that forever. So, for example, if this block exists, then all future generations, that block will still exist unless something comes and destroys it. And you say, what do you mean by comes and destroys it? Well, we'll see. I have a video that'll blow your mind. So we also have oscillators. Oscillators are structures which they start in one configuration, and the rules make them oscillate with a certain period back to the starting point. So, for example, here's a blinker, and it's just a line of 3, either vertically or horizontally, and it will oscillate between a horizontal line and a vertical line, back and forth, back and forth. So the period of that oscillation is 2, meaning that there are 2 possible shapes. Here's what is called a toad, where it sort of opens its, it croaks, so it opens its mouth, its belly fills up. Here's like a beacon. You have a pulsar. It's a complicated structure that has a period of 3, but we also have things. This is the pentadecathlon, which has a period of 15. It's crazy. A period of 15. That's a really long period to actually happen. That's the oscillators. But there are also things called spaceships, and the spaceships move throughout the array. Okay? So I know that it's hard to tell from here, but these are actually moving through the array and oscillating as they move. It's actually kind of crazy. So I have a YouTube video here. This is only a clip, like a 1 or 2 minute clip from it, but the YouTube video is called Epic Conway's Game of Life, and it shows some of the structures that you can have with Conway's Game of Life. So I'm just going to let this play for a little bit because it's really fascinating. So you can have reproducing structures like this that are producing spaceships. So if you start with one of these, one of the frames of this oscillating structure, you can produce spaceships. And if you have another one down here also producing spaceships, you can possibly have them in such a way that they end up colliding. Now, you expand that over to like a much bigger area, and the results that you get are absolutely insane, to where you actually start to look like civilizations. Look, this is so crazy. How can this possibly happen from 4 little rules? You have these generators down here that are generating gliders that come up to form larger spaceships that then go off to like invade other galaxies. How does this not blow your mind? Like, it's crazy. It's absolutely crazy that this can happen. I don't know. You think maybe, I'm just freaking out or whatever, but I want to play part of that again because it's just so insane that you can go from 4 little rules like that to these crazy oscillating gliding structures that actually reproduce, consume, form together, make structures that look like human intuitive structures or even video game structures, and then go off and like, it's just crazy. So I want you to watch this again. If you weren't blown away the first time, because the first time I saw this, like, it took me a minute. These are just array values. They're bools. And a little bit of a rule. Look at this, okay? This is just nuts. So these are being produced down here. These are being produced up here. And they're constructing a ship. And it's 4 if statements. So what this showed me is like, people say like, how can life exist? Like DNA, how does that produce life? Well, look at what's being produced from 4 if statements. Imagine what can be produced from the infinite variety of DNA and protein structures, etc. It's nuts. Anyway, okay, I'll get over it, Dave. We got to go to the next slide. So I'm very impressed with Cellular Automata and what they can do. But we're not talking about Conway's Game of Life. We're talking about CA for PCG, right? Let's get back on track. So CA have been used for decades for PCG, almost as old as Conway's Game of Life. People have been using Cellular Automata for pattern generation and texture generation, etc. So this is not a new thing, but it was new to me at some point, and maybe it's new to you. So the 2D grid cell nature of CAs make them a perfect fit for game representations, because we often work with grids, right? We've looked a lot at grids. So someone just in the chat just asked, what is PCG? Procedural content generation. We're talking about that in this lecture. So there's no right or wrong way to use a Cellular Automata for PCG. You take a CA, you come up with some rules, and you see if it works. You play around with it. That is the real fun of procedural content generation, is the parameter tuning and the coming up of new rules and all that sort of thing. It makes it so fun. It's kind of meta in a way that procedural content generation generates infinite content, but there's infinite ways to generate infinite content. So you can play around with it forever. So it's like, it's infinite down and infinite up. It's really interesting. So let's look at just one way that we could use a CA to generate a cave-like 2D terrain for game maps, okay? And we're going to be using, keep this in the back of your mind, that you're going to be using this for assignment 3, okay? So there's many ways that you could use a CA for terrain generation. I want to phrase that as many times as I can and drive it home and make it really clear that we are only using one very specific way to do that in this lecture. There are many other ways, and you are, in your assignment, you are free to use any way that you want that produces an interesting result. However, what I'm going to show you is from this particular website. Now, this website didn't invent this method. This method's been around since the 70s. In like old mud, like Unix terminal games used to use this for generating caves for their RPG games and stuff. But it is like the simplest possible algorithm, and you'll see just how simple it is. So the website has a live demo and some Java code. And so you can use that Java code and translate it to C++ pretty easily. But I'll be showing the demo in a little bit. This method can be used for the assignment, and the really cool thing is that it's going to use rules that are very similar to Conway's Game of Life. Okay, in that it's going to count things that are alive or dead and then produce a next iteration based on that. So just like Conway's Game of Life, this method will decide on which cells live or which cells die based on which neighbors were alive or dead in the previous generation. And that's it. That's the whole algorithm. Now, like, that's it. Literally, that's the entire algorithm. You're going to look around, you're going to count the number of alive or dead, and you're going to apply 2 rules. It's so simple. I have never had anyone have a problem with this part of the assignment before. So here it is. The rules for this particular generation algorithm Well, here's how it's going to work. First of all, it's going to start randomized. So we're going to create an array of random values, zeros and ones, and then we're going to apply this rule iteratively. And what you see here, it's going a little bit fast, but as it iterates, it's going to be making the initially random environment more and more intuitively cave-like. Okay. It's going to depend on 4 values. So we're going to have 4 variables that we use with this algorithm. So very simple algorithm, 4 variables. The first one I'm calling chance to start alive. So when you first initialize your grid, you're going to put random values into that grid. And when you iterate through, you're going to go for each x and for each y, what is the probability that that cell is alive or not? Okay? So this chance to start alive, if it was 50, then every time you encounter a new cell, you're going to generate a random number with a 50-50 chance that it's alive or dead, or 0 or 1, or true or false. If that was 20, then every 5th cell, approximately, would be alive. So this is the chance to start alive. Death limit. This is a variable, just like Conway's game of life, at which it's the lower limit at which cells start dying if there's overpopulation. Okay? The birth limit causes cells to become alive, and the number of steps is the number of simulations or iterations of this cellular automata that we will use to produce our final value. It couldn't be easier. And let me show you the entire algorithm in, well, okay, including the signature, it's like 10 lines of code. It's crazy how good this is. All right, so this is a function. This is going to be like pseudo C++. It's not exactly C++, but what we are going to do is we're going to say do simulation step, okay? And this is going to be called this many number of times, right? So the number of steps to perform, each frame of this animation is one of these simulation steps. And I'll show a live demo of this so we can step through it a little bit slower. So this function is called do simulation step. You are going to pass it in the previous grid value, right? So you've got a grid that was either the initial grid of random values, or maybe it was the grid after the 3rd iteration or whatever. And what you're going to do is you're going to create a new grid. You're going to fill it out with the newly computed values. And then as the return from this function, you're going to return that newly generated grid. So you are not going to be modifying the old grid. You are going to create a new blank grid and fill that out. And the reason for that is because if you were modifying the old grid, then you would be changing the values of that grid while you're computing it, and the result would not be what you want. And if you ever try and do that or work it out in your head, you'll see very quickly why you need a new grid to store things in. Okay, so what we do is, and again, for people who are new to the lectures, grid here is essentially a 2-dimensional array of integers or booleans or whatever. So a grid is a 2D array. Then for each x, y in the grid, we're going to have this value, and just for space, this is neighbors. Okay, so NBS is neighbors, and that's going to count the number of alive neighbors surrounding x, y in the old grid. All right, so you loop through, you count the number of neighbors that are alive, and you store it in that variable. Really, really easy. Then you have this if statement. So 3 lines of code here. If cell XY was alive in the old grid, then we do this condition. So if it was alive, we have to decide whether or not it stays alive or whether it dies. So if the number of neighbors around this cell in the previous grid is less than death limit, then you kill the cell. Okay, so whatever it happened to be, if it was alive, then the new grid's XY value is going to be false. So if you got integers, it's going to be 0. If you have booleans, it's going to be false, right? Otherwise, if the number of neighbors is greater than or equal to death limit, you're going to say it lives. Easy. Well, this was the condition for whether or not we were alive in the old grid. So now we have to see if you were dead in the old grid, do you come back to life? So, if the cell was dead in the old grid, if the number of neighbors is greater than birth limit, then in the new grid, you're reborn. Okay? Otherwise, you stay dead. That's it. And you return that grid. So it really couldn't be easier in terms of, like, as long as you can manipulate the values of a 2D array, you can implement this algorithm. For people who are not in the course, I apologize that the code, the assignment is not going to be open because this is really going to be a cool assignment. But please go play around with this, and in a minute I'll post an assignment, or I'll post a URL where you can actually play around with this. So we saw those parameters, right? One of the benefits of this method is that we have complete control of those different variables. So, for example, we could make the map appear more or less densely populated. So down here we have really dense caves, and up here we have really sparse caves. And that's just a value, that is a function of those parameters. So for example, if we start with very few alive cells, so the chance to start alive, if we put that down really low, maybe we make this, where it kind of looks like a lake with some islands, for example. Or if we start with a lot of noise, maybe then we have more like a cave-like structure. So it's really interesting what we can generate. So in the assignment, what we're going to do is we're going to give each planet unique variables for variety based on the planet seed. And I know that I haven't talked about you're like, what planet? Well, I just wanted to put that in there so when you do get the assignment, you can refer back to this. So now we're going to show a demo of this being done, and it's a really cool demo. So let's pop up this website, and I'll paste it in the chat so everyone else can play along. There is the URL. And this was actually written by Michael Cook. Michael Cook is a colleague of mine. I would consider him a friend at this point. He does procedural content generation for games, but he takes it, he takes it to the next level where he makes procedurally generated games. Like the rules of the games, the content for the games, everything he does is like the whole game is generated. So, Games by Angelina is his website where he talks about, let me post that as well, where he talks about this sort of thing. Okay, so let's look at this. What am I doing here? Sorry about that. Someone had a question. I had an idea of a puzzle game where you can, based on a CA, where you can solve puzzles by setting the rules of the CA to meet a certain goal. Yep, you can do all sorts of really cool stuff like that. Okay, so generating caves with cellular automata. Here we go. So let's create a new world. And what we want to do is here we have the birth limit variable, the initial chance variable, the number of deaths, and the death limit, okay? So let's, for example, generate a new world, and we can do more simulation steps with the cellular automata to see how the world views itself. So if we put down the initial chance to be alive, then what we do when we do simulation steps, initial chance applies to all cells, yes. So initial chance just means what is the initial chance that, number of steps. So new world, here we go. If I put number of steps down to 0, what we see is the randomness that we're starting with, all right? So if initial chance is equal to 0.5, then what we have is a half and half chance that whenever we generate this, one cell is on or off. If we put this all the way up to like 90, we start with a ton of cells that are on. Let me see if I can make this a little bit bigger. No, not really. The weirdness of the website doesn't let me put it a bit bigger. So that's the initial values here. So let's say we put it to 0.4. And then what we do is we have the birth limit of 4, the death limit of 3, and we do simulation step. And we come up with this really cool structure. Okay? Let's see if we put the birth limit down and the death limit down. So the death limit should always be lower than the birth limit. Okay, so let's generate a new world and we'll do some simulation steps here. And what we see is the type of cave structure that we have is much more dense to the point where it's maybe not even connected anymore. So these values, let's put the birth limit up to 5 and the death limit to 4, do simulation step. Okay, maybe we put the death limit down to 3 and we get really sparsely populated caves. So the really cool thing is that we can generate lots of interesting terrain with these methods. Okay, and this goes into a complete tutorial. If you didn't quite get it from the lecture, you can follow this tutorial to your heart's content. So let me go back to the slides and please play around with that lecture. Okay, where is the PowerPoint? Here we go. Perfect. So we showed this slide already. We showed the live demo. So that's what you're going to do on your assignment. This is like half of the assignment is this. Super easy stuff. Here's another part that I put in here where CAs are not just for generating 2D grids or 1D grids or fractals or Conway's Game of Life. They are being used for lots of cool stuff. One of the things, if you go to this website, there is actually a demo that you can use to generate music with Cellular Automata. So lots of cool stuff going on in PCG with Cellular Automata. Okay. Second part of this class is on Perlin Noise. And Perlin Noise is super fascinating because it can do some really, really cool stuff. All right. So what is Perlin Noise? Starting with random data. So we saw how we took a random grid of values before, and we used a cellular automata to generate interesting structures from that. We're going to do the exact same thing with Perlin Noise, except it's going to maybe look a little cooler, right? Perlin Noise is a little bit more interesting, I think. So the output of Perlin Noise is often used in procedural content generation as a sort of height map to generate terrain. And I'll show you kind of what this means later. And so Perlin Noise can be used to generate data in any number of dimensions. Now, I had this question. Someone knew that we were going to be talking about Perlin Noise and asked me on Discord, why do they call it noise? And I thought that was an interesting question because it's maybe not obvious to everybody. So what do we mean when we say noise? Noise usually means like me talking could be noise to someone, right? It's some sort of sound. And noise implies it is an unwanted sound. It's a sound that's annoying or doesn't really mean anything, right? So noise can be thought of as sound without pattern. It's just volume, essentially. So originally, please say something in the chat. I know I'm dating myself. If you ever used a television that got its signal from the air. So not digital, like not a satellite, but like an actual antenna that you had to move around. Now, this is a little bit kind of like, this is kind of when I was born, like the late 80s, early 90s, this was still happening. So like you have the bunny ears, right? Like Mr. Bean trying to find a signal. So not everyone has done that. So originally, radio and television frequencies, right? They could experience these random values of interference. And that would produce, when you turned on the television, a literal noise, right? So it would be a noise on the signal that the user could hear. And it would be kind of randomized, like shh, right? And you could call it static, but it was a noise. And they called it a noise on the signal or a noisy signal. And the reason they called it noise is because it had no pattern. It didn't mean anything. It was just whatever. Yeah, so go to your radio. And if you have a radio that you can tune, if people still have a radio or in your car, just tune it to a station that isn't a station, right? So we've got like 97.5 K-Rock We've got 99.1, hits FM, whatever. But in between that, if you go to like 98.2, you're going to get static, right? So that's why it's called noise. So in the literature, in, going on from that point forward in history, whenever you say noise or a noisy signal, if you're doing signal processing, or random noise, it just means random values. So that's what it is. Okay. So why is Perlin noise interesting if it's just random values? Well, it's not, okay? Perlin noise has some interesting properties that makes it really, really cool for humans to play around with. So here's an example of one-dimensional noise. So what this is, it's a X and Y plane, okay? And what we've done is for every X value, we've generated a random Y value and just connected them with lines. All right? And what we see here is not very interesting. If you connect random points with lines, this is what you get. This is true random noise, okay? This is true random values. However, Perlin noise is going to generate something a little bit more pleasing. It's got a randomized starting seed, okay? But what it ends up generating will have properties that maybe that we would want to have for things like PCG. So what we can do is use, oh geez, I feel like I'm in the ocean now, is we can apply this as well, not only in one dimension, but in two dimensions. So if we have a 2D array of values, for example here, let's take the black value in this array as 0 and a white value as 1 and scale it in between and apply it to a mesh of some sort and plot that as the height of a mountain or something. So oftentimes what Perlin noise is used for in two dimensions is to give a height map for a three-dimensional structure, okay? So as we see here, you can generate Perlin noise on the fly with more modern Perlin noise techniques. There's something called improved noise that came out in like 2002. What was it, like a SIGGRAPH paper or something by Perlin? So he came up with a way to more efficiently generate values so that you didn't need to have a big array at the time. So you can use it for terrain generation. If you think about something like Minecraft, this could be used to generate like Minecraft blocks on the fly if you want to. It can also be used for texture generation. So here is a Perlin noise being used to simulate the water. Oh, sorry about the bitrate. Yeah. So here we have like, pretend this is a scene like in an ocean. And as the water comes through the waves, it's going to be dark in some areas or light in some areas on the ocean floor. So we're not simulating like ocean physics or anything here. But what it turns out is that certain parameter tunings of Perlin noise can get you values like this that allow you to generate textures for things as well. So it's not just used for height maps, but it can be, and it's often used for terrain or for texture generation as well. So Perlin noise also has various parameters that you can tune. And it is through the tuning of those parameters that you get things like really jagged surfaces, really smooth surfaces, really rocky surfaces with high variation, really low variation things. And there's lots of different outputs that you can get from Perlin noise. So the Perlin noise output, typically, you're going to get a value that's between 0 and 1, okay? So you take that value between 0 and 1, and let's say that you have a height map, right? So that height map, you want mountains to be between 0 meters tall and 1,000 meters tall. Then you would take 1,000, you would multiply it by the value that the Perlin noise gives you out, right? So that's how you'd use it. Or if you're generating a texture, for example, those values can be interpreted as grayscale values. And so you could have a color and you say like value times 255 because like the RGB are between 0 and 255. So you could say if you get your value out and you multiply it by 255 and you're creating an RGB color, then this is your grayscale color. You could also interpret these values as a height map and color them in interesting ways or scale them in interesting ways to produce realistic terrain. And here's just an example of different ways to take these values between 0 and 1, okay? And then you have some sort of key or legend or color scaling that you use where all you have to do is assign values from 0 to 1 to whatever color you want, and you can produce all sorts of cool stuff. You can produce clouds, you can produce fire, you can produce terrain, and I'm going to show a live demo of this in a little bit. So, I struggled. I was up. I know that you guys see me on Discord at like unreasonable hours. I had about 15 slides of Perlin Noise code and explanation and everything just done up, and I was not satisfied with it. I did not do Perlin Noise the last time I did this course, and sometimes you do not succeed in the way that you want to when you want to teach something. And I am very upfront in my failings as a teacher, and I just did not feel like the way I was explaining it was proper. So what I did was I said, rather than me create like 400 slides and spend a month trying to explain it properly, because it's a hard concept to explain properly. And I'd go and I'd steal code from websites, and I'd, go to 10 different websites and try and average the way that they explained it, etc. I'm just going to give you 2 websites that I thought were really well done, okay? And here's the thing. On the assignment, you can get full marks by doing the Cellular Automata. You can get bonus marks if you use Perlin Noise. Okay, so we're going to be generating planets, and I'll show this all on Thursday when I explain the assignment. But if you use the Cellular Automata, which is dead easy to implement, you can get full marks on the assignment doing that. However, if you use Perlin Noise, there are bonus marks because it's a little bit more complicated. So I included these 2 links in the PDF, okay, and take a screenshot if you want. But what What I am about to show you is the code that I implemented from looking at this first example. Okay, so what I did was I took that code, it's sort of pseudocode, sort of C-like, sort of Java-like, translated it into a C++ class, threw it into a user interface, and made sure that it worked for you all. So all of this ended up being me like going to bed at like 4 in the morning, stressed out about Perlin Noise. I hope you're not disappointed that I don't have the slides with it. Hopefully, by the next time I teach this, I have come up with a good way to teach it because it's difficult to do live. Let me just say that. Okay, so at least I hope that you appreciate me being honest with you. All right, so what we're going to do now is I'm going to open up my code here, and let me go back to the middle monitor. So what I've done is I have created like a Perlin class here where I've tried to do like 1D Perlin Noise and 2D Perlin Noise, and I have implemented that into the following user interface. Okay, so here's what I generated, and I apologize if my bitrate goes down. So here we can see I've made this like scrollable, and you'll have a very similar interface to this for assignment 2. So what I did was I generated, I think it's like 512 by 512, like a pretty large 2D array of random values. So for each pixel here, we can zoom in. All right. For each pixel here, I've essentially drawing a tile to the screen, or a quad in OpenGL terms. And so for each value in the grid, I have given it a random value between 0 and 1. So that 0 and 1 gets translated into a grayscale value by just taking the 0 to 1 and drawing it as RGB. So let me show you the code that draws that. Okay. So you don't necessarily need to be too concerned with this, but if you do Perlin Noise for the assignment, maybe you want to. So here is the part of my rendering code where I go through the grid. I can ignore this value for now. I don't actually use it anymore. So I go through the 2D grid and I want to draw the grayscale value. Excuse me, I gotta sneeze. Okay. So I'm gonna go through each value and I'm going to draw that little tile for each gray value. And I have a little Boolean here, and we'll talk about that in a second, whether or not I want to draw a grayscale value or a color value, and I'll show you the color value after I explain the grayscale value. So each of the values in that grid I can get by saying grid.getXY. That gives me the floating point value. Now, in SFML, which is the graphics library that we're using, your colors are going to be defined by integers. So I have to take that value between 0 and 1 and convert it to a value between 0 and 255 and make sure that that's an integer. So that's what I've done here. I took the value between 0 and 1, multiplied it by 255, converted it to an integer, and then create a grayscale color to display. That's what happened, okay? So let me show that again. Okay, so that's what I did here. Now, let me show you first an example of Perlin Noise happening, which I've built in. I have some keys here that I can play with. So, Perlin Noise, and I'm not going to go over all the details of the algorithm. The details of exactly how it works and why it works as well as it does is many, many pages long, okay? One thing I will semi-explain to you, that one of the ways you will understand the code easily, but someone asked, shouldn't we round the number? The conversion to an integer does the rounding for us, so we don't need to worry about that. In one dimension, what Perlin Noise is doing is it takes your array of random values, smooths them in interesting ways, chops them up in a sort of iterative manner, and then sums them while taking weighted averages of various places in it, okay? So, for example, you're going to take your curve, if you will, and depending on the frequency and the number of octaves that you use, etc., you're going to chop it in half, duplicate it, and add the values. Then, iteratively, you chop that half into halves, duplicate it again 4 times, add the values. You chop those quarters into eighths, duplicate it 8 times, and add those values. And you're smoothing it along the way. The reason I'm not explaining it is because I want you to read this article. It's better than the slides that I could create from it. And to introduce you to 2 variables. One variable is the number of iterations that we apply the Perlin Noise technique. And what it does is, like I said, it halves it, doubles it, and then adds it to itself. That's called an octave, all right? The second value, we can think of as, some people call it a bias, some people call it a smoothing value, etc. There are just 2 values that I want to talk about. There are other values in more complex versions of Perlin Noise, but the number of octaves and the smoothing value are the 2 that I really want to show you. Okay. So if the number of octaves is 0 or 1, depending on how you implement the algorithm, what you have is just your noise. Okay? Now I'm going to press the key to increase the number of octaves by 1. And you can see what's kind of happened is almost like a blur effect. All right? So let's zoom in and see what's happened. This is 0. This is 1. 0, 1. Okay? 0, 1, 0, 1. Now, let me press it again. And as I keep pressing it, it like blurs the blur of the blur of the blur. Right? That's how I look at it. So this is what we get. Jesus, voice cracking. When we go, oh, I went too far, from random noise, 1 octave Perlin calculation, 2 octaves, 3 octaves, 4 octaves, 5, 6, 7, 8. Okay? So we can get some really interesting thing. I think maybe this is pretty interesting. Okay? So let me use this to show you the other factor which is the smoothing factor, if you want to look at it like that, or the bias factor. So I have another key which can decrease the bias or increase the bias. And so what the bias does is it smooths things a little bit more. So if I put the bias all the way down to an unreasonable value, what we get is something that's like so smoothed out and so blurred and averaged that we probably wouldn't want to use it. As I increase it, we can see that it looks more and more and more textured. Actually, I think this starts to look like Factorio to me. This like I get reminded of playing Factorio from just looking at this, okay? So if we increase it too much, though, it starts to look random again, right? So this is a few octaves into the Perlin calculation, but the smoothing factor is down so low that it's not really interesting anymore. So let's put that back to something more interesting. So this is what the output of the Perlin noise is going to look like. Now, how could we use this to generate something that looks like a video game level? Well, what we can do is very simple. We do one of the coloring techniques that we saw before. So if I just really quickly open up the slide and I look here, so for example, if we scaled the value between like yellow to red to black, then we would get something that looks like fire. But what I wanted to do is the following. So let's look at this and let's turn this into a video game map somehow, or an environment that we could look in. So what I want to do is I want to say, if it's a dark value, so we've got values between 0 and 1, right? So let me see if I can go back. Can I bring back up the blackboard? Okay. Let's undo all this. So I've got values. This is going to be 1 up here. And this is going to be 0. Now, let's say that I actually had like an environment, and that environment, a cross-section of that environment looks something like this. Okay? So that's my environment. Now, maybe if this is like a real-world environment, for example, there is something called sea level. So let's say that sea level is something like this. So let's get a different color. Let's do that like blue, I guess. And so let's say we want sea level to be like right here. So we're just going to draw a line across where we think sea level should be. And then so if that's sea level, anything below sea level should be water, right? That's exactly what I'm going to want to do. And anything above sea level is going to be terrain. Now I need to go back over here and finish this, and then I can do this. So this is what I'm going to want to do. I'm going to want to generate a terrain where anything below sea level looks like water, anything above sea level looks like grass or whatever. Now, I've done this in a way that I'm not exactly up to 0 and 1. So let me just move 1 down here. Or let me, I know what I'll do. I'll make this mountain a bit higher just so I have that example. Okay, so let's bring this down. Okay, and we'll go over a little bit of math. Not too much though, hopefully. Okay, so now I have this, and this is sort of what I want. So what I'm going to have is I'm going to have like a water level value. And that water level value here, let me put this in white. Why isn't that in white? Come on, white. Water level equals, and what is it here? 0.3? Let's just call it 0.3. When it comes to the actual RGB value, maybe this is 0.3 times 255, and what is that? Like 85? Something like that? That's my 0.3 times 255, whatever that is. But what we've done is we've chosen a value here, which is meaningful in a way that a certain amount of our terrain is going to look like water, and a certain amount of our terrain is not going to look like water. Okay, so how do we make things look blue? If we want to make things look completely blue, then we're going to have an RGB value, right? So our SF color, if we look at the blue value, someone said 76.5. Thank you. My mental math is terrible. So this is RGB, right? We have the red, green, blue color space that we're working in. And these are values between 0 and 255. So we can go 0, 0, 255, and that will make everything, all the water, look blue. So what we can say is something like, if the value at the current grid cell, if the value at the current grid cell is less than water level, then color equals blue. We can do that if we want, but maybe we want to go like one little step further. And we say, okay, water that's deeper should be darker, right? So what we could do is we could actually say, if the value is less than the water level, then the color equals, and we'll C equals color, and let's see what we'll do, okay? So we only want it to be blue, so we can set the red and green values to be 0. But now we want to scale the color of the water based on its depth, right? So water that's like right up at the surface will be bluer, water that's deeper will be darker. So if we put this at 255, it will be as bright as possible for the water. If we put it at 0, it will be as dark as possible. So maybe we could say something like, if we take 255 minus, so we know that the value of water is always going to be below the water level, right? And so we could do like 255 minus water level plus value, or something like this, that scales the color value based on the value, but within the color that we want. So let me show you how this ends up working out in what I've actually implemented. So here, what I have is the Perlin noise, and then if I hit a button, it turns into color. And how crazy good does that look just right away, just from implementing this? And I'll show you the actual code, okay? Now, if we look at this and we say, okay, what does it look like if I keep putting in more Perlin noise? Well, it gets kind of smoothed out, right? But you can see that it ends up being, like, we can generate so many different types of terrain. Like, this looks like maybe like a marsh or a swamp. And this looks like continents or something like that. Not only that, but I could put in a button that raises or lowers the water level, which I did. So let me hit a button here. I'm lowering the water level, so there are fewer cells that should be colored blue. Now I'm raising the water level, right, to generate this terrain. And it's so simple to do. If I hit the R button here, I can generate a new random seed that it starts with. And then I can say, okay, maybe I want there to be like islands for this map. Or I'll bring down the level of water so that there's a land mass that I can pass through, right? It's just so cool what you can generate with this. And also, if I look at the smoothing values, if I turn the smoothing value way up, we get something pretty gross. I really wouldn't want to play this. But if we turn it too far up, then what we get is essentially indistinguishable from randomness again, right? So we wouldn't want to do that either. So there's a sweet spot in here somewhere, right? And we tune the parameters, and we turn the amount of water up or down so that we get exactly what we want. And we have an infinite amount of content. Now we could zoom in on this, and maybe what we could do if we wanted to actually play within this peninsula, maybe this is St. John's Harbor or something like that, you know, we could generate this at like a higher resolution. We could take this and then regenerate it in a hierarchical fashion or whatever. But I took this from this website. So the first website here, it's the exact code from that. Okay, it's super simple to implement. If you want to do that for your assignment and make your planets look like this, you will get bonus marks for that. Okay, but you can just do the Cellular Automata if you want to get your quick and easy assignment marks. Okay, so let's look quickly at the code that I ended up using for that. So what I did was I got the value from the grid as a value that was originally between 0 and 1. I put it between 0 and 255. Then I created a color variable. I said if the value of the grid was less than the water level variable, it starts off at like 128 or something, then what I have is 255 minus the water level plus the value, okay? And that just scales it from not black, but kind of a blue up to a given value. And then all I do is if it's above that value, I take the value and just put it straight into the green to create the grass. And what you see is that the stuff it creates is like remarkably good. So here again, if I apply the coloring to the randomness, this is what we get, right? So it still works on the randomness, it's just that this is kind of unappealing. So then we apply a few iterations of Perlin Noise. We move the water level maybe down a little bit, right? Maybe another iteration of Perlin Noise. Great. Now I have the world that I want to play my civilization or risk game on or something like that. Okay. Awesome. So again, I want to apologize for my slight failure to not truly get into the nitty-gritty of the Perlin Noise. However, I am also a believer that some things you can just implement without knowing all the details of, and you get great results. And that is probably going to be about 90% of your programming careers, is Googling Perlin Noise and implementing it, right? So let's just take it with a grain of salt and move forward. So we'll go back here for a second. How to use Perlin Noise in your games. This is what I did. I looked through this. I literally did this. I copied this into my C++ code and then modified it so it was actual C++ code. Be careful though, the HTML formatting missed up here. So you're going to see some things where it's like ampersand GT. That's, if you take this here, that's a greater than. So this should be greater than or equal to. And also there's some less than or equal to's as well. So that's what I did there. And it ended up working. They go into more details about how you can take Perlin Noise to blend two things together. So for example, if you had grass and you have road and you generate some Perlin Noise, you can apply the grass texture to the road texture at the sort of the borders to create a nice smooth blend between two textures using Perlin Noise. Okay, so you see here, this will create the areas where you actually want to do the nice smooth blending. So many cool things that you can make with Perlin Noise. And also, if you had a 3D game, you can just have your mesh generated from a height map using Perlin Noise. This article goes into all of that, terrain generation, world generation. It's so cool. And please, this is like, me telling you to go read the textbook. And I highly encourage you to explore Perlin Noise to its fullest. So if we go back here, that was CAs and Perlin Noise. On assignment 3, it's going to be up to you, which you use to generate the planets. The universe is going to be generated in a static way. Let me actually show you what the assignment will look like before I go. So I'm going to my YouTube channel here. I have a video of it. I don't currently have the assignment running, so this is going to be... let me get the video up. Okay. So this is assignment 3. We are going to be generating a universe that has star systems, and you can scroll around this universe. When you click on a star system, it has a number of planets that you can explore. You can select one of the planets, which I'm doing right now, and visit the planet, and that planet will have a given size and a terrain that you can visit and pan around on. Okay? So one part of it is the random number generation using the Lamer RNG that we talked about last time. And the second part is the planet generation, which you can either use the Cellular Automata or you can use the Perlin Noise that we talked about. In this assignment, this version in the video, it is just using the Cellular Automata. And so you could make your planets look a lot nicer maybe than the ones that are here. And the really cool thing is that this is a truly procedurally generated universe that you can scroll infinitely to like the limits of the double precision, and nothing is stored in memory. This is all being generated on each frame that it's being displayed. Okay, so you could zoom out. Let me just see. Do I zoom out? Yeah. A truly infinite universe that you can explore. And so for assignment 3, we are actually like creating No Man's Sky, but without the 3D, without the 3D-ness. And so I also recommend that you could put anything you want onto the planets. So someone just said, I'd love to combine the planet generation with the GA to generate life on the planets to fit their characteristics. Perfect idea. So if you end up wanting to do the planet generation with CAs, you could put extra stuff in there, like treasure or fuel or whatever you want to do. That is all bonus marks on the assignment. Okay? So that's the assignment. I think it's pretty fun. It was pretty well received last year. And it's pretty cool how these sorts of things are so easy to do once someone explains it to you. All right, awesome. So that's it for this lecture. Thanks for sticking around. I really enjoy this kind of stuff, and I hope you're going to have fun with the assignment. Come back next class, because that's when I am explaining the assignment. And remember that Thursday night, the night that I give out assignment 3, is the night that assignment 2 is due. I apologize that the marks for assignment 1 are not out yet, but we will have those to you this week. So thanks again for tuning in, and I'll see you on Thursday.